So, welcome back everyone to the second part of the lecture. In this part, we will continue from where we stopped in the first part. We will continue with the demerits of complexity-based key approach. We will explain them one by one, starting from the first point, which says Eve is assumed to have limited computational power resources in this case. That's one of the major demerits. And why do we consider this a demerit? Because in this approach, in this category, is sign R based, which is keyless. Keyless means there is no shared key between the transmitter and receiver. Complexity based approach, there is a key. You use the channel as a source of randomness to extract a key that can be used at both the transmitter and receiver. So here, Eve is assumed to have limited computational power resources. Why? Why Eve is assumed like that? Because it's key-based approach. Key-based approach. At the end of the day, we are using the channel to extract a key. This key is a sequence of numbers that you extract from the channel and then you use to encrypt the data and decrypt it. If Eve has a quantum computer, super powerful fast computer with lots of memory, lots of CPU, lots of hardware components, GPUs, and infinite storage space, then Eve will be able, maybe in the future when we have quantum computers, will be able to crack the sequence of bits by doing exhaustive search process, brute force attack, we call it. That's risky. That's not good. That's a disadvantage. Now, how can we mitigate that? If we think, okay, this is a disadvantage, how can we mitigate that? Means not completely avoid it, but make it a little bit less of a disadvantage. I mean, mitigate it in such a way that you make it less susceptible to this kind of behavior or this kind of demerit. One way is to make sure that you don't use this extracted key more than once. Okay, you extracted this key. I have one packet that I want to send. I use this key to manipulate this packet and then send it to the receiver, and the receiver uses the same key to decrypt this packet. Okay, that's good. We agreed on it. But then if the transmitter uses the same key again to encrypt another subsequent packet, another following packet, the same key, and the same key for the third packet, and the same key for the fourth packet, this will become too much risky for the system. Why? Because you are using the same key with different packets and transmitting. You are not updating your key frequently. So what are you doing essentially? You are giving attackers and eavesdroppers more time to know what the key is, because you are using it with many packets and you are opening the opportunity for eavesdroppers to use analysis attacks, which is really bad because it can't guess the key. And to avoid that, I could generate and use only one. I could use the key once with each and every packet. So for this first packet, I use this key 1, and when I reach the second packet, when the time comes for the transmission of the second packet, I again, as a transmitter, try to estimate the channel again and extract a new random key that's different from the first one and use this key 2, let's say, to encrypt this data. And then for the third packet, I again, as a transmitter, I try to measure the channel to get another random sequence that I can use it as K3. And then I use K3 to manipulate the data. So this is really what should be done to avoid to avoid giving an opportunity for Eve to guess the key. So this is related to the first demerit. The second demerit says key length is limited with the channel variation. Thus, perfect secrecy is hard to achieve. That's really also, what does this mean? Key length is limited with the channel variation. Thus, perfect secrecy is hard to achieve. Let's explain it by drawing. So, assume you have a bucket of 100 bits, just 100 bits, which is not practical. Usually we have packets of in kilobytes and so on, but let's, for simplicity, 100 bits. This is packet, and the channel that the transmitter tries to measure is something like almost this. As you can see, there is not much randomness in it. The channel is correlated. I mean, this value is very close to this, very close to this. There is no much sudden change in the behavior of the channel. Thus, perfect secrecy is hard to achieve. In this case, what do you do? If you try to extract random keys using quantization from this channel, the number of bits, the number of bits that you can extract from this channel is limited to, let's say, just 20 bits. So you are forced to use just 20 bits to manipulate just 100 bits. Now, since the key length here, the key length, which is the random bits we extracted from the channel, is less than the packet length, you cannot achieve perfect secrecy. Because to achieve perfect secrecy, you need the key length to be at least equal to or greater than the message length. Now, what's even more challenging is when you want to transmit your second packet and still use the same key to encrypt the second packet because the channel didn't change much. So if you are in a very stable wireless channel and you are trying to extract randomness from it, but the channel is not changing sufficiently, is not changing, it's almost constant. You extract certain random bits and you are forced to use them to encrypt packets with length that's far greater than the key length that you extracted from the channel. And you may be forced to even use the same extracted key to encrypt subsequent messages multiple times, which is again can make eavesdropper susceptible to analysis attack and brute force attacks. That's what we mean by this approach doesn't usually, it's hard to achieve perfect secrecy. To achieve perfect secrecy, you always need to have a random key that has length equal to the length of the message, and you only use it once. And for the second packet, you extract another key with at least a length that's the same as the message length, and you use it for once and then you throw it away, you don't use it. This is really difficult in real life scenario. Difficult from many aspects. Difficult from the sense that the channel doesn't change much that frequently. The randomness in it sometimes is limited because the channel is not really sufficiently random. And even if the channel is sufficiently random and you are able to extract certain bits, implementing this approach to provide perfect secrecy is very costly because both the transmitter and receiver need to have this key exactly the same, with the same value, exactly with the same values, and need to use it only once with each packet, decrypt and encrypt and decrypt each and every time with a new sequence of values, which is really challenging and very hard. It causes delay, it causes extra power consumption, and it can complicate the process of having light security for Internet of Things applications, for example. That's related to point number two. What about point number three? It says that this approach, this category that we call key-based or complexity-based approach, is sensitive to channel estimation and reciprocity mismatch error. This is really good point. What do we mean by it's sensitive to channel estimation and reciprocity mismatch error? So I told you the transmitter and receiver, each one of them estimates a channel, yes? The transmitter estimates this channel and the receiver estimates this channel, but they usually, sometimes I told you, yes, the channel is reciprocal between them. Reciprocal means the uplink and downlink. If from Alice to Bob and if from Bob to Alice, they have the same channel response. But usually, there is a mismatch between the uplink and downlink, a slight mismatch. Now, if you are using higher order quantization, tight quantization, which means you are producing more bits from each and every sample, in this case, there will be some errors between some mismatch between the transmitter and receiver. The values you extract here are not the same as the values you extract from here. Okay, so because of that, this mismatch can create keys that are not exactly the same. And if the keys are not the same, what do we have? The receiver will not be able to decrypt what the transmitter encrypted for it. That even if there is a mismatch of one bit, it cannot decrypt the message back. So this is risky due to what? Due to the fact that this approach is sensitive to channel estimation and reciprocity mismatch error. Channel estimation, if it's not accurate at both sides, it can produce different keys, and if we have different keys, we will not be able to decrypt our data successfully. So we have techniques that can fix that and make sure, even we can talk about these techniques later in the coming lectures, to make sure that the key that was extracted at Bob is the same as the one at Eve, and we don't have any errors or any mismatch. Now, why do we have this match? I told you one reason is because there is a delay between the estimation of this at the transmitter and that at the receiver. Sometimes there is interference in the downlink more than the uplink. Sometimes the hardware components here at the transmitter are not the same as the hardware components at the transmitter are not exactly the same as at the receiver. And if they are not the same, they also affect the channel parameters estimated at both the transmitter and receiver, and therefore the downlink estimation will be different from the uplink estimation sometimes. And because of that, you end up extracting keys that are not exactly the same. They have some mismatch and differences between them. So this is related to sensitive to channel estimation. And the fourth point says the following: secrecy can be broken if Eve is able to know Bob's channel. So what do we mean by that? Secrecy can be broken if Eve is able to know Bob's channel. That's very obvious. If Eve knows Bob's channel, then in this case, what do you have? This is Alice transmitter, this is the receiver Bob, and this is the attacker Eve. Or so here, if the channel estimated at the receiver is the same as the channel estimated at Eve, not the same, it cannot be the same. But if Eve somehow was able to estimate the same channel as the receiver, in this case, both of them they have the same channel. And what will happen now? Both of them they have the same channel. What will happen now if they use the same algorithm to extract a random key? They will end up having the same common shared key. And if they have the same common shared key, it will be problematic because whatever the transmitter encrypt, the receiver will be able to decrypt, and Eve as well. Now, there are ways and method, very complicated ways and method for Eve to know the receiver channel, but these methods are not so easy to implement and deploy. If Eve is very close to the receiver, they will have some correlation. This correlation will make the extracted key from both sides very similar, but not exactly the same. But if Eve manages to get the same channel as the receiver or knows their key at the receiver, the whole security algorithm will be broken. And Eve in this case will be able to decrypt whatever the transmitter sends to the receiver. And the fifth point says the following: the fifth demerit, the fifth disadvantage. It says that this key-based approach, complexity-based approach, requires processing at both sides, the transmitter and receiver, which results in power delay and overhead cost. Now, we assume this as a disadvantage compared to the first category that says we can provide security without sharing keys. Now, this requires sharing keys and requires processing at both the transmitter and receiver. In the other approach, this approach that we explained last lecture, we don't have to have keys at both sides. We can only have some processing at one side, and the other party can be left without any processing. This results in power delay and overhead cost. Power delay and overhead cost, because especially for Internet of Things devices, because both whenever you want to transmit any packet, you need to do some processing at the transmitter, some processing at the receiver. And finally, it's limited to TDD systems, time division duplex system, because I told you in time division duplex system, the channel estimated from the transmitter to the receiver is using the same frequency as the one from receiver to transmitter, and because of that, the channel will be similar in the uplink. The channel in the uplink will be similar to the channel in the downlink. But in FDD system, frequency division duplex system, the channel in the uplink will use one frequency, and the channel in the downlink will use another frequency, and therefore they will have a mismatch, and they cannot extract the same random bits that can be used as a common shared key between the transmitter and receiver. So these are the overall disadvantages and demerits related to complexity or key-based approach. And with this, we can conclude our lecture. And if you have any questions, you can ask me. If you don't have, we can stop here, and we can see you in the next lecture. Thank you.